All right, we're going to be working through section 6.2 of the book, which introduces some more properties of matrices and operations, including addition, multiplication, and then finding something called the determinant and inverses for matrices. So we start off with kind of where we've been before, where we had some basic operations. We're going to learn how to multiply them and then use these things called determinants and our properties of inverses to basically help us down the road solve systems of equations. So these will be the key terminology that we look at. We've seen some of them before. The really key new one that we have here is our determinant. We haven't seen that piece before, but we'll see that that's going to be just some general mechanics that we move through to help us determine whether a system of solutions is going to be solvable or not. Again, remember that a matrix is just our coefficients for our system of equations, and that we're going to try to solve these using matrix operations. All right, so this looks scarier than it is. We're talking about how do we multiply matrices. And basically, if we remember two things, we take a row times a column, and that's going to allow us to get a value. One thing that has to work for matrices to be able to be multiplied is that the inner dimensions have to be the same. They have to match up. So if we look at what we have here on our values, so we have here a M by R matrix and an R by N matrix. So that would look something like this, M by R, and then the other one is R by N. And these two values have to be the same for this to work. So those inner dimensions have to be the same. What's going to happen is our outer dimensions, the M and the N, are going to become our resulting matrix. So we'll get an M by N resulting matrix. So if we were to look at what that looks like in our values here. So if we wanted to look at something, if I had a matrix that was 3 by, oops, let me write a 3 better, 3 by 2, and then a 2 by 1 matrix, that is going to work because the 2's match up, and our resulting matrix is going to be 3 by 1 as we go through it. And again, the 3 is our rows, the 1 is our columns. So we'd have 1, 2, 3, like that. It'll make more sense as we look through some examples. One thing to notice here as we do this is if I have a 3 by 2 and a 2 by 1 matrix, so if I have a 3 by 2, I said that worked. So a 3 by 2 and then a 2 by 1, that is valid. That's okay. If I've changed the order though, if I did a 2 by 1 and I try to multiply with a 3 by 2, we can see those inner dimensions don't match, which means we're not going to be able to multiply those. So when you're multiplying numbers and we have 4 times 5 is 20, and we have our commutative property where 5 times 4 is also 20, that doesn't exist for matrices. We can't just flip the order of our multiplication. It has to be where those inner dimensions match up. All right, so let's look at an example. All right, so we're going to look at how these work. We're going to have our two matrices here. We can see at the top, we have a 1, 2, 3 rows, so that is 3. And then it has 2 columns, 1, 2, 3 by 2. This one over here for B, right, has 2 rows by 3 columns. And since these inner numbers match up, we're going to be able to multiply them. So we'll look at what those mechanics look like here. So it is going to work, and we should be left with a 3 by 3 matrix at the end. So the way that we go through this is we're going to take row by column. So what that means is we take the 4 and the 5 and then the 7 and the 2. The 4, the first thing, and the 7 match up, they multiply together, and then we add the second one, the 5 and the 2, they multiply together, and we're going to get a number. So for all of these, basically we're going to take each place. So this is the first row, row number 1. This is column number 1, and that's going to place in our resulting one the first row and the first column, and we'll get a number there. If we were to look at the second one, so if I want that second piece, if I do the second row and the first column, that's going to be the second row, first column, and those values are going to go down here. So I'm going to do 1 times 7, and I'm going to add the 9 times the 2. Right? So again, they match up first to first, second to second, and we just repeat that operation until the whole thing has been created. So I do then the third times the first, and that would work. And then I would move on to the second column. So I do first row, second column, and then I do first row, third column. I'd work all the way across until I've gone through all my different permutations of how those could exist and place them in the resulting matrix. When we do all that, what we're going to see is that we have all our values. So we continue going through each row and each column, and by the time we're done, that's what it would look like. So we've gone again each row times a column, and we've placed them in the appropriate piece. We can see here that we have a 1, 2, 3 rows, and then 1, 2, 3 columns. So a 3 by 3 final matrix. And again, that came from a 3 by 2, and then a 2 by 3. The inner dimensions matched up, and the resulting outer dimensions, 3 and 3, came down here for our resultant matrix. And then we'd have to just simplify, and we'd have our final matrix. And back. There we go. So the 38, 30, this piece here is our multiplication of those two matrices. All right. So for part B, we want to see if this will work. So when I look at our matrices here, we have a 2 by 3 and then a 3 by 2 because they exist. So we have that inner dimension that lines up, right? 2 by 3 and then 3 by 2. Since this matches up, it's going to be able to be multiplied, and then our resultant multiplication is going to be a 2 by 2 matrix. So we again go through the same mechanics that we had before, where I take row times column, the 7 goes to the 4, the 0 goes to the 1, the 1 goes to -6, and we add them up, and that becomes our first piece. So we go through those values again, and we would get pieces added up, and finally get there. Here we go. We've done each row times each column, and we can see that what we have is 1, 2 rows, 1, 2 columns for a 2 by 2 final matrix. And then we simplify those results, and we would get our final multiplication. So that one worked both ways, where we could do A times B and then B times A. That's not always going to be the case, again, depending on what it looks like. In terms of those dimensions, they have to match up. All right. There we go. All right. So what I want you to do is you're going to pause the video at this point, and you're going to go to your assignments. So you're going to go to your homework. We just worked through example 1A, and then you're going to do the guided practice problem here for example 1. So go ahead and pause the video, and then see if you can do A times B and give me the final matrix there. All right, so you've worked through the guided practice problem. Hopefully that made sense. We have some properties of multiplication for matrices that we want to look at. So first one is that we have our associated property. We'll basically have 3 things, A times B times C. I can do A times B first and then times C, or I can do A after I do B times C. So the parentheses there can move around. I have a scalar property, so if I just have a number in front of it, I can multiply A and B first, or I can multiply A first and then times B, or multiply K and then times B. I have a distributed property where I can take something outside the parentheses and multiply it through, and then I get there, and I have it on the right side as well. What you notice that I don't have is my commutative, where A times B equals B times A. That does not always work for our properties of matrices.